So this problem says that we have refrigerant 134A. It's at well, basically, let's just say what the problem's doing. So we have refrigerant 134A that's flowing through, it's flowing through a pipe that is basically being cooled by air. So basically we have a heat exchanger. And I'm going to draw, so this is, let's just say that this is like a duct or something that has air flowing through it. And then we have this pipe with the refrigerant flow that goes through this duct, or whatever it is. So we have refrigerant flowing through this smaller pipe, and then we have air flowing through this duct. And so basically this refrigerant is flowing through here, and as it flows through there, it's being cooled by air. So we have a heat exchanger, and that gives us some property data for the inlets and outlets of the air and the refrigerant. So I'm just going to write that down. And this is the part of the problem that I'm calling the setup. And you want to do this, like you'll want to set up all of your problems just so you have a really clear idea of what's going on, and you know how you're going to solve the problem. So first of all, it says that the refrigerant 134A at 1 megapascal and 90 degrees C is to be cooled. So that means that at the inlet, let's just make this more clear. So at the inlet, the pressure of the refrigerant, and I'm just going to call it R for refrigerant, so P1R, so 1 is for the inlet, and then it's refrigerant, so P is 1 megapascal, and then T1R is equal to 90 degrees C. And you can call these variables whatever you want, just make sure it's something that makes sense. Otherwise the problem gets kind of confusing. Okay, so we have the inlet for the refrigerant, and it says that it's cooled to 1 megapascal and 30 degrees C. So at the outlet we have P2R is equal to, so the pressure doesn't change, but the temperature is lower, so T2R is equal to 30 degrees C. Okay, and then it says the air enters at 100 kilopascals, so we have the air, and I'm going to just call this P1 air, so I'm going to use consistent terminology. So the air is at 100 kilopascals, and the temperature is 21 degrees, so T1 air is 27 degrees C. So the air enters at 100 kilopascals and 27 degrees C. It tells us the volume flow rate, so we have V1 air is equal to 600 meters cubed per minute. So just don't let this confuse you. The volumetric flow rate isn't a conserved property. So the volumetric flow rate is likely going to change between the inlet and outlet of the air, just because air is compressible. So don't think that the volumetric flow rate is 600 meters cubed per minute at the inlet for the air. It's probably not equal to 600 meters cubed per minute at the outlet. Okay, and then it says that the air leaves at 95 kilopascals, so P2A is equal to 100 kilopascals and, 95 kilopascals and 60 degrees C, so T2A is equal to 60 degrees C. And then it says determine the mass flow rate of the refrigerant. So we're looking for the mass flow rate of the refrigerant. And so that will bring us into our assumptions, because we're going to assume that this is a steady flow problem or steady flow process. So if you think about if you think about it, the refrigerant and the air both have to be flowing as steady flow. Otherwise, you would have air or refrigerant accumulating or disappearing from your system. So let's say this is our system. So basically, if this were in startup or shutdown, that might be the case. But since it's not in startup or shutdown, we're assuming it's been operating for a while. We're going to assume that the mass of the refrigerant isn't changing with time inside the control volume, and the mass of the air isn't changing with time inside the control volume. So what that means is that we're going to assume that the mass of the refrigerant in, the mass flow rate in, is equal to the mass flow rate of the refrigerant out. So then this is just equal to the mass flow rate of the refrigerant, which is what we're looking for. And we can make the same assumption with the air. So if we assume this is steady flow, we're going to say that the mass flow rate of the air in is equal to the mass flow rate of the air out. So we just have the mass flow rate of the air. And this is where you don't want to get confused with this volumetric flow rate. The mass is conserved. Like, we know that mass is a conserved quantity. So if this is steady flow, that means that the change of mass inside the system with time has to be equal to 0. But the volumetric flow rate, like volume, isn't a conserved quantity. So the volumetric flow rate is going to change unless you make an assumption that you're dealing with an incompressible substance. And air is definitely compressible, so we can't make that assumption. All right, so we have some assumptions. Let's make a few more. So basically with these assumptions, we're assuming steady flow. I'm also going to say, so the air is ideal gas. It's at a pretty low pressure and high temperature compared to the critical pressure and temperature for air. So air is ideal. And that means that we can assume constant specific heat. And we're also going to assume, well, the change in potential energy is going to be 0. I think that's pretty clear. There's not going to be a large elevation change over this heat exchanger. Even if there is, we haven't been given any data about it. So we have to basically assume that it's 0. Most heat exchangers aren't going to have a huge elevation change, but if you have one that happens to have a large elevation change, you might need to consider the potential energy. So just make sure you read the problem statement carefully, or in real life when you get into your job, if you're analyzing a heat exchanger that's like several meters tall or something like that, then you might want to consider the change in potential energy. And also, we're going to assume that the change in kinetic energy is 0. That one's a little less obvious because we have flowing fluids, and it's like, well, is the velocity changing? Well, it could be, but the thing with heat exchangers is the velocities are usually pretty slow. Otherwise, like if you think about it, if the velocities through this heat exchanger were really fast, there wouldn't be enough time for much heat transfer between the refrigerant and the air. So we actually want these to move pretty slow so that there's time for maximum heat transfer to occur. And they're also going to be relatively unchanging. And so we can assume that the kinetic energy is approximately 0. If you're given, and the other thing is we're not given any information in the problem about the velocities, so even if we wanted to calculate the change in kinetic energy, we don't have the information to do it. So this is another thing to pay attention to. You could potentially have a change in kinetic energy, but you would need to know what the velocities are. So if your problem gives you information about velocities, that's something you might need to consider depending on what the velocities are. Or in real life, you're likely going to know what the velocities are of your fluid flowing through the heat exchanger, so then you can get an idea of whether or not you need to consider the change in potential energy. Though there's no work, so heat exchangers are passive devices, and it also doesn't give us any information about heat transfer out of the heat exchanger. So basically when I say that, we know there's heat transfer between the air and the refrigerant. And so, I mean, that's pretty obvious, but what we're interested in is both of them. So our system is, and our system is basically includes both pipes. So it includes the pipe with the air and the pipe with the heat exchanger. So if we assume that this is well insulated, which is often a really good assumption with heat exchangers, in real life they're often pretty well insulated, we can assume that there's no heat transfer out of the system. So there's no heat transfer here, so Q is 0. And this can be a little bit confusing because it's like, well, there is heat transfer here, like from the refrigerant to the air, but since that's inside our system, we don't need to consider that in our full energy balance. So basically we're going to say that Q is equal to 0 because we're assuming that the heat exchanger is well insulated. So basically, in order to solve this problem, we could theoretically solve the energy balance and get a value for Q, but in this case we don't have enough information to do that. We would need to know what both of the mass flow rates are. We only know one, really. We're calculating the other one. So we don't have enough information to calculate Q. We weren't given Q. So basically we're just going to assume that the heat exchanger is well insulated and there's no heat transfer to or from the heat exchanger. So this means that it's adiabatic. And so basically and I'll just put this too, so all heat transfer occurs from the hot fluid to the cold fluid. So basically we have heat transfer from the refrigerant to the air, and we can just assume that all of the heat that's transferred out of the refrigerant is in the air. Like, we don't have any losses outside of the system, we don't have any heat coming in. So that actually greatly simplifies this analysis because we don't need to worry about Q in our energy balance. So I think that this is basically our problem set up. We have our assumptions. Now let's write down the equations we need. So we're going to need the first law energy balance and for a steady flow. And this problem is a little bit different from quite a few of the others I've been doing because with this one we have multiple inlets and outlets. So basically if I redraw what I have going on here, so we have an inlet here, outlet here, outlet here. So we have 2 inlets and 2 outlets. So we need to consider our first law energy balance so we need the steady flow equation that allows for multiple inlets and outlets. And that was derived in the video that I did on the derivation for the first law energy balance. And so go back and watch that if you want to see where this equation came from, but for here I'm just going to write down the equation. So we have Q minus W is equal to, and then we have the sum, and this is the mass out, and these should be rates. So this is, and I'm going to actually change this out to 2 just to simplify the writing. So I'm just saying that, well, this is all of the out, so let's just leave that like that. But then I'm just going to call 2 here and 1 here. So 1 is in, 2 is out. So this is H2 plus V2 squared over 2 plus G Z squared minus, and then we sum all of our inlets. So this is M dot, and then I have H2 plus V2 squared over 2, and actually these are 1 because this is the inlet. So this is actually 1, 1, and then this is over 2 plus G, Z1. Alright, so this is our general energy balance, and as you probably guessed, a lot of these terms are going to be 0. I just wrote out the entire thing so that you know what equation to start with. In fact, when I'm solving these types of problems, I always start with this equation, and then I cancel out the terms I don't need. I feel like this is much easier than trying to write down an equation for a specific case and then trying to figure out if it applies in your case. Because the equations that are written for specific cases, they have assumptions built into them, and if you just write down an equation for a specific case, it might have an assumption that you can't make, and it might be hard to figure that out just by looking at it. So I like to start with this equation. This is the general energy balance for steady flow. So if you don't have steady flow, you'll need to be starting with a even more general equation than this one. This one, we've assumed that all of the time derivatives are 0 because we don't have anything changing with time in our system. So this is the equation you'll start with for a steady flow for multiple inlets and outlets. So now let's figure out which terms are 0. We've already assumed that it's adiabatic, there's no work, and we've said that all of the change in potential and kinetic energies are 0. So basically almost all of the terms are 0. I also like to write down these equations, and then when I cancel out everything I don't need, it leaves you with a much simpler equation. But let's just write down this. So if M out is multiplied by H2, and using 2 on these was probably a bad idea. I'm just going to change these to out. So these are out, this is in, and then same thing on these terms, just because it was probably kind of confusing to write it like that. So H out, and then we have minus, and then the sum of the inlets. So this is in, this one's out, and then H in. So this is the equation this is our energy balance that we can use for this particular case of this heat exchanger. And the reason why I like to start with this equation is because if you just write down this equation, which you can, but if you just write down this equation, you have to sit and think, okay, what is this assuming? Okay, this is assuming that it's adiabatic, there's no work, the potential and kinetic energies are 0, it's steady flow. There's just a lot of assumptions built into this second equation, whereas this first one, the only assumption built into this first equation so far is that it's steady flow. So it's a much more general, non-specific equation to start with, and if you start with it, you're going to almost always get the right you're almost always going to get the correct energy balance for your particular system. All right, now let's write in our actual inlets and outlets, and I'm going to use the terminology that I had before. So just draw this again. The hardest part with these heat exchangers is to just keep track of everything. So the more little drawings and things you can have to kind of keep track of things, the easier it's going to be to get it set up. So I'm going to call this, so this entrance here is 1 refrigerant, so that's in, so 1 refrigerant. This one's 2 refrigerant, so the outlet refrigerant. This one's 1 air, and this one's 2 air. So now let's go ahead and expand these summations for our specific problem. So we know that we have 2 outlets. So our first outlet is MA, and remember that M2A is equal to M1A, and I'm just going to call this MA, and the reason why is because we're assuming this is steady flow, and the same thing with the refrigerant, so M2R is equal to M1R, and I'm just going to call that MR. So I'm just going to have MA here, and this is the outlet, so the So the mass flow rate of the refrigerant at the outlet, and then this is multiplied by the enthalpy at the outlet for A, plus, and then we have the refrigerant, so MR, and then this is multiplied by the enthalpy of the refrigerant. And then we have minus, and then we want to sum our inlets. So we have the mass flow rate of the air multiplied by the enthalpy of the air at the inlet plus the mass flow rate of the refrigerant multiplied by the enthalpy of the refrigerant at the inlet. So now what I want to do is combine like terms, so where I have this mass flow rate of the air and mass flow rate of the refrigerant. I want to just combine those to make this a little more concise equation. So 0. So all I'm doing now, this is basically my equation. All I'm doing now is moving some things around to make it a little bit easier to read. So I have the mass flow rate of the air multiplied by the enthalpy of the air at the outlet minus the enthalpy of the air at the inlet plus the mass flow rate of the refrigerant multiplied by the enthalpy of the refrigerant at the outlet minus the enthalpy of the refrigerant at the inlet. Okay, so we have our energy balance, and let's just take a step back, and what we want to do at this point is determine what we're looking for and what we already have. So first of all, we have so if we go back up to our problem statement, we have the mass flow. We weren't given the mass flow rate of the air, but we were given the volumetric flow rate at the inlet. So we can use that volumetric flow rate to calculate the mass flow rate at the inlet. And then since we know the mass flow rate at the inlet is equal to the mass flow rate at the outlet, we basically have the mass flow rate of the air. So we're just going to calculate that, and we're going to calculate that from the mass flow rate is equal to V1, so the volumetric flow rate at the inlet divided by the specific volume. And since this is an ideal gas, we can just calculate this volume from the ideal gas law, so PV is equal to RT, and we know that V is equal to RT over P. So we have everything we need to calculate the mass flow rate of the air, so basically we know that. So if we go back down to this problem, so this is known once we calculate it, and I'll just rewrite that here. So the mass flow rate of the air is equal to the volumetric flow rate, and I'm going to actually be a little more specific. So the mass flow rate of the air at the inlet is equal to the volumetric flow rate of the air at the inlet divided by the specific volume of the air at the inlet. But we know that this is also equal to the mass flow rate of the air at the outlet, so that's why that's just equal to the mass flow rate of the air. And then since we assume that this is an ideal gas, we can calculate the specific volume from the ideal gas law. So the volume is just equal to RT over P. We know the temperature, pressure. We can look up the gas constant. So we have everything we need to calculate the mass flow rate of the air. So we're going to basically assume that that's known. This is what we're looking for. So we need to figure out a way to get the enthalpies. For the enthalpies of the refrigerant, we're just going to look these up on the tables. That's pretty easy because we're given all of the property data that we need to look those up. And then for the enthalpies for the air, we can do this a couple of different ways. Since this is an ideal gas, we know that the change in enthalpy is equal to C sub P T2 minus T1. So we can calculate this using a specific heat, and then we would just look up the specific heat at the average temperature, and we know T2 and we know T1, so we can calculate that. The other way that we can do this is we can look up the enthalpies So look up H2A and H1A on the air table. So there are two ways that we can calculate this. I'm going to use the specific heat, but just so you know, you could also look up those values on the air table and you would get the same answer basically. And if you want to verify that, you can solve it both ways and just verify that you get the same answer both ways. Alright, so it looks like we basically know what we're doing to solve this. We're solving for the mass flow rate of the refrigerant. We're going to look up the enthalpies of the refrigerant on the tables. We're going to calculate the change in enthalpy of the air using a specific heat, and we're going to calculate the mass flow rate of the air from this relation. So now let's get our data. And like I said, the hardest part about doing these heat exchanger problems is just keeping track of everything. So just make sure you label everything and try and keep things really organized, and you'll find that these problems are a lot easier. So the way I'm going to look up the data, I'm going to first do the refrigerant inlet, so R134A inlet, and at the inlet we have that P1, this P1R, is equal to 1 megapascal, and T1R is equal to 90 degrees C. So basically we can determine from these values that this is in fact a superheated vapor. So we need to get our enthalpy from the superheated vapor table. So HR1 is equal to 324.66 kilojoules per kilogram. All right, now let's do our outlet for the refrigerant. So R134A outlet. We have the P2R is equal to 1 megapascal, and T2R is equal to 30 degrees Celsius. If we look up the saturation temperature at this pressure, we'll see that this is a compressed liquid. And since we don't actually have a compressed liquid data table for this temperature and pressure, we're just going to assume that it's a saturated liquid. So basically HR2, actually 2R, is equal to the enthalpy of saturated liquid at 30 degrees C. And remember to look it up on the temperature table and not the pressure table. So this is 93.58 kilojoules per kilogram. All right, now let's do the air. Well, I'll write down the data for the air inlet and outlet, even though I'm using a specific heat. But anyway, the air inlet, so we have the P1A is equal to 100. And actually, we don't even need the pressures to look things up on the air table. We just need the temperature. So T1A is equal to 300 Kelvin. This was 27 degrees Celsius. And so from the air table, H1A is equal to 300.19 kilojoules per kilogram. And then the air outlet, so T2A is equal to 60 degrees C, which is 333 Kelvin. H2A is equal to 333.33 kilojoules per kilogram. And then we also need, so we have the data from the tables, we also need the specific heat. So like I said, this is enthalpy data from the air table, and you can either solve this problem using the data from the air table to get your change in enthalpy, or you can use the specific heat and just calculate the change in enthalpy. So I'm going to do it with the specific, actually I guess I'm going to just do it both ways. So so the specific heat of air, and I'm going to use an average temperature of approximately 300 degrees C. That's not the exact average. Well, I guess actually I'm just using the temperature of the inlet, but there's not a huge change between the temperatures, and basically the reason why I did that was because if I look at the data for air, I have data for between 300 and 350, and I'm going to be, like, the average of this is somewhere around 315, and the specific heat only varies between 1.005 and 1.008. So basically, I'm just using 1.005 kilojoules, kilogram, Kelvin. Although if you wanted to interpolate and get a more specific value, there would be no problem in doing that. I just think you would end up with probably about the same answer. So let's also, well, I think this is all the data we need. Well, we need R, so we need our gas constant. And we need the gas constant for air, so that is 0.2870 kilopascal, meter cube, kilogram, Kelvin. Okay, now we have all of our data, we have all of our equations. All we have left now is to plug numbers into the equations and solve. So I'm going to go back to, I'm going to rewrite the equation, or I'm going to rewrite our energy balance that we're solving. So m dot A H2A minus H1A plus m dot R H2R minus H1R. And then what I want to do is, well, first of all, I want to plug specific heat, our specific heat relation into this equation. So this is going to be Cp T2 minus T1. And then I just want to solve this equation for the mass flow rate of the refrigerant, because that's what we're actually interested in. So if we do that, we have negative Ma and then H2A minus H1A is equal to the mass flow rate of the refrigerant, and then we have H2R minus H1R. And then I just want to multiply through this negative sign. So if I do that, I get Ma dot H, and I forgot to replace this with the specific heat. So this should be C sub P T2 minus T1. So this is C sub P T2 minus T1 is equal to m dot R, and then I'm just going to swap the signs on these two enthalpies. So I have H1R minus H2R. And then this means that the mass flow rate of the refrigerant is equal to the mass flow rate of the air multiplied by C sub P T2 minus T1 over H1R minus H2R. Or if we didn't assume specific heat, so let's say we just get data from the air table, then the mass flow rate of the refrigerant is equal to the mass flow rate of the air multiplied by H2A minus H1A divided by H1R minus H2R. So do you see how you can kind of solve this two different ways? Really, all we're doing is trying to get the change in enthalpy. You can get the change in enthalpy from table data if it's available, or you can calculate it using like specific heat. So now let's calculate the mass flow rate of the air. So the mass flow rate of the air is equal to V1A over the specific volume, and we need to calculate the specific volume. So from the ideal gas law, It's just RT over P. And then we should have everything. So R is 0.2870 kilopascal meter cubed kilogram Kelvin multiplied by 300 Kelvin divided by 100 kilopascal. So then the kilopascals cancel, kelvins cancel. We're left with meters cubed per kilogram. So the specific volume is 0.861 meters cubed per kilogram. So then we're going to plug this into here, and we know the volumetric flow rate because it was given. So the mass flow rate of the air is equal to 600 meters cubed per minute divided by 0.861 meters cubed per kilogram, which works out to 697 kilogram per minute. I'm going to convert minute into second because that's a little more standard. So 1 minute over 60 seconds. So then the mass flow rate of the air is equal to 11.6 kilograms per second. All right, so now we have everything we need to plug into either of these two equations and solve. So we know the mass flow rate of the air, we know the specific heat, we know the temperatures, we know the enthalpy of the inlet and outlet of the refrigerant. We also know the enthalpy of the inlet and outlet of the air, and then just the refrigerant. So let's go down here and solve these. So we have the mass flow rate of the refrigerant is equal to 11.6 kilograms per second multiplied by, and this is the one with the specific heat, so 0.05 kilojoules kilogram Kelvin multiplied by 60 minus 27 degrees C. And we can do this because the delta K and delta C end up being the same. So if we're just subtracting them to get the difference, we don't need to convert to Kelvin. So, and then divided by 324.66 kilojoules per kilogram minus 93.58 kilojoules per kilogram. And just to specify the equation, since it was off the screen, the equation for this is the mass flow rate of the air multiplied by the specific heat multiplied by T2 minus T1 over H1R minus H2R. So this is the equation that I'm solving here. So now let's make sure our units work out. So the kilojoules cancel, this kilogram cancels, and the Kelvin cancels, and we're left with kilograms per second, which is what we want. So this works out to 1.66 kilograms per second. Now let's just verify that we could have also solved this with the equation using the specific heats of the air, or sorry, the enthalpies of the air from the air table. So that equation was the mass flow rate of the air multiplied by H2A minus H1A divided by H1R minus H2R. And so I don't think I'm going to go through and plug all of those values in again. Well, actually, maybe I will. So this is equal to 11.6 kilograms per second multiplied by, and then H2, the enthalpy of the air at the outlet was 333.33 kilojoules per kilogram minus 300.19 kilojoules per kilogram divided by 324.66 kilojoules per kilogram minus 93.58 kilojoules per kilogram. So let's just make sure the units cancel out again. So this these kilograms all cancel, the kilojoules all cancel, and we're left with kilograms per second. So this works out to 1.66 kilograms per second. So we got the same value with both methods. Basically what I want you to see is, like, if we go back to our energy balance, so this, basically this is what we end up with for our energy balance. And we're often left with a scenario where we need to calculate delta H or delta U. And basically there are different ways that we can do that. We can look them up on the tables if the tables are available, or if their tables aren't available, we can calculate those using specific heats. So however you do it is fine, just be really clear about what you're doing. So basically the way we did this problem was, first of all, we wrote down all of the information from the problem in our setup, figured out exactly what we were solving for, what was going on. Then we made some assumptions, and the assumptions are really important because they tell you basically what equation you need to use. I mean, we know that we need to use this steady flow energy balance equation, but what if you don't know, and I didn't get the whole thing. I mean, this is a huge equation. We don't want to solve this entire thing by hand. Plus, we don't have all of the information to even solve this entire equation. So basically, we need to make assumptions so that we can make this equation solvable, and also simplify it so we can get a reasonable answer fairly quickly. So that's why we need to make assumptions, so we know what we can cancel out of our equations and get an equation that's solvable. With a lot of engineering problems, if you don't make assumptions, the only way to solve your equations is with a numerical solution, and that's not very convenient if you just want a really quick answer to something. So anyway, we did the equations, and then we looked up data on the tables, and we solved this problem. And these problems from here on are going to start getting a little more complicated, and actually complicated is the wrong word. They're just going to start having more things that you need to do, especially when we get into the second law. You're going to have to start solving for entropy as well as some of the other things we've been solving for. So doing these problems in a really ordered manner like I've done here is going to really help, because these problems are going to get really confusing really fast if you're not approaching them in a methodical manner. And so this is how I like to do them, and this is how I recommend doing them. Anyway, I hope this was helpful. Thanks for watching.